Okay, guys. So the topic for today is on the board. And guys, it's at this point that we can talk introductorily, if that's a word. We can talk up front about the purpose of this entire unit. So guys, this unit on reaction rates, guys, as far as the AP authors are concerned, and make sure you catch this, as far as the AP authors are concerned, guys, this unit has one and only one purpose. And I couldn't tell you about this last time because we hadn't discussed it yet, but we're going to talk about it today. And I want to at least lay this before you so you always have the big picture in mind. So, and I'm even going to write this into the title for the notes. So if you titled the top of your notes, you may want to write this down as sort of a subtitle to your notes. Because guys, this is the bottom line. So what are you going to see on the AP test? What are you going to see on our tests? Well, we've already said you're going to be writing rate expressions, right? But what did we say about rate expressions? You're going to forget about them. And why are you going to forget about them? Guys, the reason you're going to forget about them is we're going to spend the rest of this unit writing rate laws. So you're going to find out what a rate law is in a minute, and you're going to learn to write them. But rate laws are not going to be an end unto themselves. And guys, this is what you want to write down. What you are going to be asked to do with rate laws is, first of all, you are going to be asked to write them. And that's what you're going to learn to do today. And you're going to like this. The logic is wonderful. So guys, you're going to learn to write rate laws. But that is not the end of the game. Once you've written a rate law, guys, the next thing that you're going to be asked to do is verify whether the rate law is actually valid for the reaction. And guys, in order to do this, you are going to learn to understand what are called mechanisms. And guys, we are going to talk at the end of the day today about what mechanisms are. I'm going to ask you to not take notes, and I know that makes you nervous, but you're just going to have to trust me. Guys, today you're going to learn to write rate laws, and then when we're done with that, we're just going to call time out. I may even ask you to put your notes away. Because then, guys, I'm going to give you a real brief overview of what mechanisms are, and that's going to be all day Monday, but I find it helpful to introduce it today. But guys, here's the trick. You are going to be asked to verify these mechanisms given the rate law. But you got to know this, and I know this doesn't make a lot of sense to you right now. Proposal. You will never be asked to propose mechanisms in rate laws. You'll never be asked to figure out what they are. You'll only be asked to determine if they're correct. So guys, that's part of the reason why we have to do hypotheticals a lot of times when we do this, is because you are not going to be asked to understand enough chemistry to propose mechanisms and rate laws. You're going to be asked to verify them and make sure they make sense, but you're never going to be asked to come up with them on your own. It'll be verifying and not proposing. And I know that doesn't make a ton of sense to you right now, but guys, the idea again is this. Today you're going to learn to write rate laws. Then we're going to relate these to mechanisms, and you'll be verifying these relationships. You will not be proposing these relationships because you won't know enough chemistry to propose them, only to verify them. Do you kind of get what we're saying? It'll make more sense as we go. So guys, with that said, let's teach you how to write rate laws, and then we'll talk about mechanisms briefly. And guys, frankly, today's a pretty short day. You're gonna like this. It's interesting. Okay, so guys, let's go back and review. So if you remember last time, we started looking at rate data, right? And when we looked at rate data, we understand that we can look at data that represents the relationship between concentration and time. And guys, let's talk about what we learned. Over time, what happens to the concentration of reactants? goes down. Over time, what happens to the concentration of products? It goes up. But guys, because the concentration of reactants goes down over time, what happens to the speed of reactions over time? Okay. So guys, are you comfortable with those ideas? That over time, the reaction is consuming itself, the amount of reactants goes down, so the rate of the reaction goes down. Does that sit okay with y'all? Okay. So guys, with that in mind then, we looked at data like this. And so I'm going to zoom into this. This was the same data that we looked at last time. And we said, okay, so the data that we're given time, we're given concentrations. Do you remember what we said though? Typically, what concentrations are we given? Not of reactants, of products. But they chose to give us reactant concentrations, and that's fine. But in either case, guys, we've got time, we've got concentration. The concentration of the reactants is going down. We can figure out the rate by doing final minus initial concentration, final minus initial rate, do the math. Is all this sitting good with you? Okay, now here's the problem. And guys, the reason that I bring this up is because when you look at this data, your eye is learning to make sense of this data, and you're seeing time, and you're seeing concentration, and you're seeing rate. But guys, the thing that you're not realizing that you're seeing is you're also seeing blocking in color. So there's this weird orange color, and then there's this weird sort of gray color, and then you've got data. Well, guys, here's the thing. When you look at rate data, it's actually not going to look like this. But unfortunately, the book uses the same shading strategies, and you're going to get confused. So, guys, this is not the rate data that we're going to be dealing with for the rest of the unit. So look at what we've got. We've got time, we've got concentration, we've got rate. Got it? Okay. So, guys, now look at this. Because in order to write rate laws, this is what the data is going to look like. So now we're talking about another reaction. This is the reaction between ammonium ion and nitrite ion, and when these react together, they make nitrogen gas and water. And guys, here's the trick. This is what the data needs to look like in order for us to write rate laws. Now here's the problem. You've got the orange box, you've got the gray box, and you've got columns. And when you look at this, your brain says, oh, that looks familiar, it's got to be the same. But guys, if you dig into this data more deeply, you're going to find out quickly that this data has nothing to do with the data that you've already seen. So guys, let me switch to a pen, and then let me zoom into this. And guys, let's talk about what you're looking at here, because this is the data that you are going to be presented for the rest of this unit, and you've got to understand what we're looking at here. So guys, let me give you a second to process, and then we're going to talk, first of all, about how this data is different, and then second of all, what we learned from this data. Have you had a second to chew on it? So guys, fundamentally, how is this data different than the data that we looked at just on the previous slide? What's the difference? Oh, go ahead, sorry. That's it. Guys, do you see this? This data is not a progression over time. This is not 1 minute, 2 minute, 3 minute, 4 minute. This is not changes in concentration over time. So if that's the case, what is this data? Well, guys, let me show you what you're looking at. Remember what our reactants are. Our reactants are ammonium ion and nitrite ion. Notice that that one is here and this one is here. And then, guys, look at your last column. Last column is the rate. So we're not calculating rates. We are being given the rate of this reaction. So, guys, if we understand that this column is the concentration of ammonium and that column is the concentration of nitrite, then what is taking place as we move down through this data? It's not relative to time.
So they're changing the
Yes.
And then that's going to affect the rate. And then it's just going to be an experiment.
Exactly.
Instead of being like, here's a time 0.
Right.
Just say, okay, time 0 we had this much.
Right.
Let's put it in here. Time 3 we had this much. Let's do that.
Right. And so, guys, the bottom, and let me just summarize what Jake said well. The idea is this. This represents doing the same reaction 8 times. So if you can picture this, in trial number 1, you get 0.01 molar this, you get 0.2 molar this, dump it together, measure the rate, pour it down the drain. Then, guys, you come back and you do it again, and you get 0.02 molar this, 0.2 molar this, dump it together, measure the rate, pour it down the drain. Then you do it again, 0.04 molar this, 0.2 molar this, dump it together, measure the rate, pour it down the drain, and you do this 8 different times. In the first 4 trials, you're changing the concentration of ammonium. In the second 4 trials, you're changing the concentration of nitrite, but the only thing that they're measuring is the rate. The second they're dumped together, then you stop collecting data and start over. Do you understand what you're looking at? Does that make sense? Okay, now let's interpret it. Guys, now compare, and what we need to look for are the relationships between concentration and rate. So guys, look for those relationships and understand if you're looking at these relationships and going, duh, it's not always going to be this simple. So guys, talk to me. What are you observing? Go ahead, Brent.
Something I find interesting is that in both, so experiment 1 through 4 is
Yep.
the concentration of ammonium.
Okay.
But those same numbers are really similar to the numbers that they actually use when they're testing NO2 concentration. And you get very similar results in your rates.
So tell me more about your similars. I don't see what you're saying.
So on experiment number 1,
Yep.
you have 0.01
Okay.
concentration of ammonium.
I'm with you.
On experiment number, sorry, that was a bad example. On experiment number 2,
Oh, I see.
0.02.
Yeah.
On experiment 5, you
Yeah.
also have 0.2.
Got it. And
And the rates are the same thing.
good for you. Good. So we're seeing a connection there between concentrations and rate. And if the concentration of NH4 is this, that's the rate. If the concentration of NO2 is this, that's also the rate, so long as these are the same. What else do you see? Rebecca, you were going to say something. Good. And so Brandon is talking about specific rates. And then Rebecca, importantly, is talking about trends in relationships over time. What else are you seeing? Go ahead. Oh, sorry.
It's not like a 1-to-1 ratio. So
Right.
the fastest rate, like
Yeah.
you have the 0.2,
Yeah.
and
Right.
the fastest.
Yeah, good for you. That's awesome that you saw that. Say it again.
So look at experiment number 8. That's the fastest in terms of observed initial rate.
Yes.
And that one is not a 1-to-1 ratio, ammonium and nitrate.
But what is true? It's not 1-to-1, but you've got the highest concentration of one of these reactants, and because I think I'm still in drawing mode. So this is 0.2 and that's 0.2, so those are the same. This concentration's a little bit lower than this one, and that one's slower than that one. But you're right that it's not directly proportional. You'll find out why in a minute. Go ahead, Mark.
Well, so if you look at the difference in initial NH4
Okay.
and 2,
Yes?
it's doubled.
Mm.
Look over at the rate. It's also
Did you guys pick up on that? Doubling the concentration doubled the rate. Does that relationship continue to extend? Like, for example, if we go 1 to 4, what have we done? Or I'm sorry, trials 1 to 3, what have we done to the rate or the concentration? Quadrupled it. What happens to the rate? It also quadruples. Now we're starting to see things. Matt, you were going to say something. What's that? I stole your thunder. Sorry.
I have one question of why, when we go from 2 to 3, it doesn't go again.
From 2 to 3?
Yeah.
Okay, so let's talk. So if you go from trial 2 to 3,
Oh, that is really.
so that doubles, and that is a tenth off of doubling.
And going from 0.04 to 0.06 doesn't double because it's not
Because that's not doubled.
But if you see the 221.6
Right.
to the 43.3,
Right.
which is a doubling.
So this ratio is the same as that ratio.
Yes.
Yeah, do you see it? So guys, let's now talk about this because none of you mentioned this, but we need to make sure we're clear on this. Guys, looking at this data, what from this tells you that this was done by a scientist that has a clue about how to do science?
The numbers work out.
What do you notice? What do we call those constant? What do we call about that? What do we call that experimentally? Controls. Guys, they had controls. They said, I want to see the relationship between NH4 concentration and rate, so they kept the NO2 concentration constant. And then they said, okay, I want to see the relationship between NO2 concentration and rate, so they kept the NH4 constant. Guys, that's just good science, right? Keep one constant, change the other, and then figure out the rate. What would have happened if they were changing both simultaneously? You would know which one's changing rate. By the way, guess what? The AP authors will do that to you. They'll actually change both of them, and you're going to have to figure out which is doing which. We'll talk more about that later. But guys, now let's talk about what we really need to be able to dig out of this interesting data. So guys, this is the idea, and this is how we write rate laws. When we write rate laws, what we're trying to do is this. We are trying to figure out how changing the concentration of reactants changes the rate of the reaction. So how does changing the concentration of NH4 change the rate? How does changing the concentration of NO2 change the rate? And so in order to do that, and I love that you guys did this naturally. Did you guys notice what you were doing when you started to dig the trends and the interesting things out of the data? What was the first thing that came out of your mouth, most of you? Trial numbers. You said looking at trial 1 and trial 2, looking at trial 1 and trial 3, because you needed us to be looking where you were looking, and you did that by referencing experiment or trial numbers. Guys, you've got to do that on the test. Make sure that when you're trying to draw these logical connections, you've got to say, looking at trial 1 and trial 2, looking at 1 and 3, you've got to talk about trial numbers. But guys, the idea goes like this. Looking at trial 1 and trial 2, what is happening to the concentration of NO2? Nothing. What's happening to the concentration of NH4? It's doubling, and what happens to the rate? It doubles. So guys, what about this? What if we look at trials 2 and 3 or 4? What are we doing to the concentration between 2 and 4? Tripling it. And what happens to the rate? It also triples. So here's what we know. Any change that we make to the concentration of NH4 has a proportional change in the rate. Does that make sense? Okay, so now guys, let's go down and let's talk about the NH or the NO2. So if we go down here and look at the NO2, and again, we're going to reference trials. So notice that here, this is our control. And if, oh no, did that backwards, sorry. Notice that down here, these are our controls. And if we double that concentration, what happens to the rate? It doubles. What happens if we triple the concentration? Triples. What happens if we quadruple the concentration? What happens to the rate? It quadruples. So guys, now here's what we know. Any change that we make to the concentration of NH4 has a proportional change on rate. Any change that we make to NO2 has a proportional change on the rate. And so now you're thinking, yeah, that's what's going to happen. Well, guys, guess what? That is not always what happens. It turns out that sometimes you can double the concentration and the rate quadruples. It turns out sometimes you can double the concentration and the rate will octuple. You beginning to get a sense of what these relationships look like? They're exponential. Guys, sometimes you can double the concentration and the rate doesn't change at all. So understand in this rate data, it looks like double this, double that, double this, double that. But guys, very seldom is it that simple. We're just starting with simple data to drive home the idea. You see what we're saying? Okay, so guys, what are we going to do with this idea? So here's what we know. We know that any change that we make to this has a proportional change there. Any change that we make to this has a proportional change there. You guys all settled on that? How do we represent it? Well, guys, we represent this by writing something called a rate law. This is where you want to start taking notes. So guys, rate laws go like this. Here's what we've said. And do make sure that you include this in your notes. It's not just a subtitle. It's up to you. I mean, it's really just rehashing what we've said. So if it's helpful for you as you're rereading your notes to make the transition, the idea is this. Here's what we've established. That it doesn't matter if we increase the concentration of ammonium or nitrite, increasing either one will have a proportional change, will affect a proportional change on the rate of the reaction. So what are we going to do with this? Well, guys, we can actually represent that reality mathematically. And we do it like this. This you definitely want to write down. So guys, this expression that you wrote on the board that says rate is equal to K times brackets NH4 plus times brackets NO2 minus. This is the mathematical expression of what we figured out from the data that simply says double the concentration, double the rate, triple the concentration, triple the rate for either reactant. Are you guys all caught up with me? Not quite yet. How about now? You okay? Let me go for a second. I think your questions are going to get answered. So guys, let's do this. Do you know what these brackets mean, right? Not moles, molarity. The brackets are, do you guys know that? Brackets are molarities? Okay. So guys, what this is saying is this. The rate is equal to some constant, K, times the concentration of NH4 times the concentration of NO2. Now guys, what you just wrote down is called a rate law. So now you're going, wait, how did we come up with that? Well, I'll show you. But guys, the rate law, this thing right here, this is a rate law. And this is the rate law for the reaction that we just saw the data for. So guys, this is what is called a rate law. So let me introduce you to the components of a rate law, and then we're going to talk about what we're going to do with rate laws and how to figure them out. So guys, let's dig this thing apart. So first of all, what is a rate law? A rate law is a mathematical representation that represents the relationship between concentration and rate for a chemical reaction. So guys, if you're not seeing that, we've got concentration and rate, and we've got concentration and we've got rate. So that's all a rate law is a mathematical expression that tells us about the relationship between concentration and rate. Yeah. Oh, no. This is math. Yeah, no, this is math. So, guys, do you see the connection there? The red arrows? Concentration to rate, concentration to rate. But if that's the case, what haven't we talked about? The K. Guys, K is what is called the rate constant. No, not at all. We're going to solve for it in a minute, though. So, guys, I'm nervous to do this, but I'm going to do it. Let's see how this goes. So what is K? Well, it's a constant. But what does it represent? And guys, I'm going to lay this before you, but we're not going to dig into it deeply. But let me lay this before you. Guys, what are the 4 factors that influence the rate of a reaction? Concentration, temperature, physical, and catalyst. Okay, right? I'm not even going to spell it out. But guys, here's the deal. In a rate law, here's the concentration right there, right? And this is a rate law. We're talking about the rate of a reaction. So we've got concentration right there. Where do we have temperature, physical conditions, and catalysts? K. The value for K changes based upon the other things that change the rate of a reaction. We're going to talk about that in a couple days, but that's what K is a representation of. It's actually a representation of the temperature, the physical properties of the substance, and then maybe the presence of a catalyst. But that's how this all fits together in the big picture. We've got concentration right here, and then K is a mathematical representation of the rest of these, and we'll talk about that later. But guys, what we need to be able to do right now is we need to be able to solve for K. So we're going to do that right now. Using the data in the previous table, guys, we are going to solve for the K value for this reaction. So let me do this really quickly because this is going to make my life easier. I'm going to take this slide and I'm going to paste it down here, and then I'm going to delete this, and then I'm going to move this up, and then when I go here, we can go bump, 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 and then I can go down here, and there we've got the data. Oh, you know what though? I'm going to move this down because then I can solve up above. Okay, so guys, using the data that's in this table, we are now going to solve for the value of K. So let's talk about this before we get going. So we've got rate is equal to K times the concentration of NH4 plus times the concentration of NO2 minus. So in order to solve for K, we need to know the rate and we need to know these two concentrations. Get the idea? Okay, so here's what we're going to do. Dallin, that's your group. You guys are going to do data set 1. And Rebecca, you guys are going to do 2. Bradley, you guys are going to do 3. Valeria, you guys are going to analyze set 4. Talmadge, your guys' tables are going to do 5. And then Joel, if you guys would analyze 6. And I will analyze set 7. So guys, give it again, you know your group. So guys, take this data and analyze the data, finding K for your group. So again, it goes Dallin's group, you get it, Rebecca's group, Bradley's group, then moving over Valeria's group, coming forward Talmadge's group, and then Joel's group. Guys, run the numbers and figure out the value for K. What's that? You guys are doing 6. And guys, let me just tell you right now, 90% of you are going to get this wrong. Like you would get 0 credit on the AP test. I'll show you why. What's that? No. But why? Let's talk about this with everybody because that's really important. We'll talk. I love what you're thinking about, Mark, but let's talk about that with everybody. You guys done with your math? Okay, so I'm going to analyze data set 7. So guys, data set 7 goes like this. The rate is 32.7. No, it's not. 32.7 0.4 times 10 to the negative 7th is equal to K times 0.200 molar times 0.0606 molar. So guys, when I do that math, I don't have a calculator. I remember having a calculator. Oh, calculator. So guys, when I do the math, I get 0.2 times 0.0606, and I get 32.4 times 10 to the negative 7th molarity over seconds is equal to K times 3 significant digits, 0.0121 molarity squared. Now guys, as I continue to do the math, what I need to do is I need to move my units around. So what I'm going to end up with is 32.4 times 10 to the negative 7th molarity over seconds divided by 0.0121 molarity squared. So now we can do the math. That's easy. What do we do with the units? One of these molarities cancels with that molarity. And what do we end up with? Well, we end up with 32.4 times 10 to the negative 7th divided by 0.0121. So guys, the number's easy. That's 0.00027. What are the units? Over molarity seconds. We write it like this: molarity to the negative 1, seconds to the negative 1. Because guys, look, we have 1 molarity left in the denominator, and we have a seconds that's in the denominator of the numerator, which really puts it in the denominator. So we've got a molarity that's left uncanceled in the bottom, and we have a seconds that is left uncanceled in the bottom. Now guys, here's the trick. If you just wrote down this, you're wrong. The AP authors love to harp you on units when we're doing these types of when we're doing rate law calculations. You will see questions in multiple choice that will simply say, what are the units for K for this reaction? You'll see in the free response, they will ask you, write the rate law, then the next question will say solve for the value of K, and if you don't put units on it, you get 0 credit. Guys, why? Why are the values, why are the units for K so important? They change. The units for K are not always the same. Guys, imagine if imagine if in this reaction we had a third reactant. Let's say water was a reactant in this reaction. Well, then we would have another molarity for this reaction, and this would become a cubed, and then when we divided by it, this would become molarity to the negative 2. So guys, the units for K change depending upon the particular reaction, and they expect you to be able to track the units through the solving of a rate law to come up with the units for K that match the reaction. So guys, you've got to be able to track units through these calculations. Do you see what I'm saying? Okay, so guys, with that said, let's go back to what's really going on here, which is this, and now we've got our units for K. And guys, we understand that our value for K is 0.00027 molarity, inverse seconds. So now guys, you check your answers. They're all the same. Guys, K is a constant. Does that mean that K never changes? No, but what changes the value of K? surface area, temperature, and catalyst. If the temperature, surface area, and catalyst don't change, K does not change. But now, guys, Mark asked an interesting question that I'd like to talk with you about. Guys, what happens to reactions over time? Do they speed up or slow down? They slow down. But they don't slow down because the value of K is changing. Why do reactions slow down over time? The molarities are decreasing, and if these numbers get smaller, the rate gets smaller. But guys, you never explain it that way, right? If you were explaining why reactions slow down over time, you don't say because the molarities go down, these values go down, and the rate goes down. Because remember, reactions can't do math. What you would say is the reaction is slowing down because the concentrations are decreasing and therefore the rate of collisions decreases. But guys, we can see it mathematically that over time as these go down, the rate goes down. K does not change. You get the idea? Okay, so guys, with that said, are we all in agreement that we all got this value? Okay, so guess what you can now do with this? Once you know the value for K, you can then figure out how fast this reaction will go at any set of initial conditions. You get it? Once you solve for K, that is a constant. Just a second. And because K is a constant, you can then plug in any concentrations you want, and you can figure out how fast that reaction will go at any set of molarities. And they will have you do that in homework and on the test. So does that make sense? So go ahead.
So, it says that this is in water, 25 degrees Celsius.
Right. Yes. Right.
So is that going, and that's going to affect our K value, right?
Absolutely. Yeah. So
Is there another way to solve for K, where we just take, is there a, I mean, like, where we take, you know, because you said there were 3 things left, there's temperature.
Right.
There's, you know,
Right.
So, I mean, is there another way we can solve where we put those in?
yes, but there are other equations for K that take into account temperature, catalyst, surface. You're never going to do that in here. But the answer is yes, we just don't do it. So you guys getting this idea with K and okay. So guys, as we then said, let's go back and make sure we're clear on this because you will be doing this. So, So guys, are you okay with this idea that once you have figured out the value for K, you can then use that to solve for the rate at any other set of concentrations? Okay, but guys, the other thing we should talk about is this. When you solve for K, does it matter which trial you use? Did we all get the same answers? Yeah. So guys, it doesn't matter which trial you use, but when you do this on the test, you have to indicate which trial you're using. So you would need to say, looking at trial 1, here's the math. Or look, it doesn't matter. You just have to indicate the one you're using. Okay? Okay. So now, guys, we got to pick off one more thing, and we're done with rate laws. So guys, if you remember, we talked about the idea that in the simple example that we looked at, doubling the concentration doubled the rate, right? But guys, seldom is it that simple. So now we need to talk about something called reaction order. You want to write this down in your notes as well. So guys, what we're about to talk about is the fact that many times doubling the concentration of a reactant does not double the rate. And now we need to talk about what are called reaction orders. So guys, we understand this, right? Rate laws are rate is equal to K times concentrations. But the thing that I haven't told you about is that there's also exponents. Yeah, and we're going to allow M and N to represent these exponents. But guys, what does this mean, ... out to the right? Just keeps going. So if there's 2 reactants, it looks like this. If it's 3, you'd add another. 4, you'd add another. But guys, the thing that we need to talk about are the exponents. And guys, these exponents are what are called reaction orders. The exponents, M and N in this case, are what are called reaction orders. So what is a reaction order? Well, guys, reaction orders represent the relationship between change in concentration and change in rate. So what does that mean? Y'all caught up with me? Not yet. How about now? You okay? Okay. So guys, what are we talking about? Well, in the previous reaction, we doubled the concentration of NH4. What happened to the rate? It doubled. Doubled NO2, what happened to the rate? It doubled. That is what is called the first order relationship. Double one, double the other. That's called first order. But guys, typically, many times, these are not first order. So let me show you all the things that we're going to run into. There can be what are called zero order reactants. And if you have a zero order reactant and you double the concentration, the rate doesn't change. Let me make this a little bigger. So if you have a zero order reactant doubling the concentration, the rate doesn't change. How can that be? We'll talk on Monday. But guys, this is what you're accustomed to. This is what you saw in the previous example. These were what are called first order reactants. Ammonium and nitrite were first order reactants. What that means is you double the concentration, it doubles the rate. You triple the concentration, you triple the rate. You quadruple, it quadruples. It is a direct one-to-one relationship. That's called first order. Now guys, we can also though have second order reactants. And if you double the concentration of a second order reactant, the rate quadruples. But it doesn't stop there. You can also have third order reactants, and if you double the concentration of a third order reactant, the rate octuples. But guys, doesn't that kind of make sense? Because these numbers right here are actually exponents. So any number to itself is raised to the first power is that number. Any number raised to the second power is squared, like 2 to 4. Any number raised to the third power is octupled, like 2 to 8. So guys, these are exponents. The 0, 1, 2, 3, and 4 are 1, 2, and 3. We won't do fourth order. They're exponents, and it talks about the relationship then between concentration and rate. Yeah?
Are we just going to use positive integers, or are we going to use any decimals?
No, interestingly, yeah, these could be fractional. We're going to keep them. The AP gods will keep them whole numbers. Yeah, no, it is very sweet of them. All right. So, yeah, good question. So, guys, then what we can do is this. We can then add up all these reaction orders and talk about the overall order for the reaction. So now, guys, let me show you what we're talking about. So we've got rate was equal to K times the concentration of NH4 plus times the concentration of NO2 minus. That was the rate law for the previous reaction. Now, guys, let's talk about reaction orders. When we doubled the concentration of NH4, what happened to the rate? It also doubled. That tells us that this is a first order reactant, and we don't write down the 1. I'm going to put it there as a placeholder, but guys, if you've got a first order reactant, you don't write down the 1. Now, what happened when we doubled the concentration of NO2? What happened to rate? It also doubled. So what does that tell us the reaction order of NO2 is? Also first order. So this is the way we would say that. We would say in this reaction, so in this reaction, NH4 is a first order reactant, NO2 is a first order reactant, and the reaction is second order overall. So adding up the 1s gives us the overall reaction order, and that would be second order. So now you guys ready for a deep thought? Try this on for size. The overall reaction order gives you the units for K. Do you see that? The overall reaction order gives you the units for K. So guys, check this out. The idea is this. This is first order, this is first order, but the units for this was molarity, the units for this was molarity, and we said the rate is molarity per second. This is K, and we multiply those together, and that's molarity squared, right? And then when we divided, we moved the molarity squared over here, and one of these canceled, and we ended up with inverse seconds, inverse molarity, right? Now guys, what about this? This was not the case, but what if? What if this reaction proved to be second order in NH4? First of all, what would that look like? If we doubled the concentration of NH4, what would happen to the rate if NH4 is second order? It would quadruple. So say that that's what happened, so we know that NH4 is second order. So what are now the values for K? Well guys, now we've got this. Rate is still molarity divided by seconds. Here's our K, but now we've got molarity cubed. Do you see it? We've got molarity squared here, molarity to the first there. You multiply those together and you get molarity cubed. So now when we divide by molarity to come up with our value for K, only one of these cancels and we end up with a 2. So what would the units for K be? Inverse seconds, molarity to the negative 2. Do you see that? So guys, and you'll be able to play with this in homework, but functionally realize the units for K are determined by the reaction order of the reaction. You just scratching? You okay? Go ahead, Trace. Say that again. Oh, which one of these is first? No, not at all. Doesn't matter. No. Okay, so guys, what are we now going to do with this? Well, guys, here's what's going to happen, and we're going to solve one in the book. What we're going to do is we are now going to take a look at an example in the book, and we're going to figure out how this game is played. So guys, this is what you're going to see on the, well, part of what you're going to see on the test. But you will be asked to write rate laws in the test, and this is what this is going to look like. Looking at page 568. Here's what it says. It says the initial rate of A plus B turning into C is measured. Using the data, first of all, determine the rate law for the reaction, then figure out the rate constant, then figure out the rate of the reaction when A and B are these. So guys, the first thing that we've got to do, part A, is write the rate law. So here's how you want to approach this. The first thing that you want to do to write the rate law is write, and do this with me, you want to write as much of the rate law as you possibly can. So the rate law is going to be equal to K, and then we need brackets to represent the concentration of our reactants. And in this case, we've got A and we've got B. So that is initially as much of the rate law as we possibly can do. So now what do we need to figure out the rest of the rate law? Reaction orders. So guys, look up at the data that's given, which is just like the data we had on the board before, and figure out the concentration rate change relationships for A and B. Do you see them? So let's talk about them. Guys, let me model this for you the way that you need to do this on the test. So let's think through this. Do we have controls? Where do we see A controlled? Which trials? 1 and 2. Do we have B controlled? Where? 1 and 3. So here's how we're going to approach this. And guys, you got to say it just like this. Referencing trials 1 and 2, where A is the control. You need to say that. Referencing trials 1 and 2, where A is controlled, what are we doing to the concentration of B? Not just changing it, doubling it. And what happens to the rate? Doesn't change. So guys, this is the way you would write this. You would say referencing trials 1 and 2, where the concentration of B is controlled, doubling the concentration of A has no effect on the rate. Therefore, what is the order? Did I say that right? Yeah, keeping A constant, doubling B has no effect on the rate. Therefore, B is a blank order reactant. What order is it? 0. And you could just for now put a little 0 there. B is a 0 order reactant. Then guys, now we need the order of A. So which trials are we going to reference? 1 and 3. So referencing trials 1 and 3, where B is our control, doubling the concentration of A has what effect on the rate? Quadruples. So we would say doubling the concentration of A quadruples the rate. Therefore, A is a what order reactant? Second order reactant. And now, guys, we know the reaction orders. So here's the question. What do we do with the 0 order reactant? What is any number raised to the 0 power? 1. So we get rid of it. So guys, the rate law for this reaction is simply this. You okay? Now guys, we're not going to solve the rest of it, but I think if we talk about it, you'll get it. So the rest of this says, we figured out A, we figured out the rate law. B says this, calculate the rate constant. How do we do that? Get the rate, get the concentration of A. Doesn't matter which trial we use. Nope, solve for K. But guys, what about this? Without doing the math, what are the units for the rate constant going to be? Let's see. So yeah, so this is molarity over seconds. This is K. This is molarity squared. We'll divide by the molarity squared. Here, one of them cancels, and it's inverse seconds, inverse molarity. And then you'll need to know the number. Then guys, notice what it goes on to ask you to do in part C. Figure out the rate of the reaction at this new set of concentrations. What do? Just plug the value from B in for K and solve for the rate at that new set of concentrations. No, plug in K. So from part B, you'll have the numerical value for K. So you'll plug this in for K, you'll plug in the new concentration of A, and then solve for that rate. Is that okay? Yeah.
So I know this is a little different, but like when we were talking in the electron unit about inverse seconds, we call them hertz.
Yeah.
So
Is there a no, don't do, no, they will kill you. Don't do that. No. No. Hertz per molarity. Yeah.
So the actual order reactants the reaction orders, those don't affect K. Other than.
They affect the value for K. They affect the units for
They
K.
don't affect it.
They don't affect the value. The value for K is a function of temperature, those things.
Yes.
Yep. Okay. You guys, oh,
Well, it's gonna change, right? Because if you have that, you have a squared, and you put that under your value, instead of being divided by 0.2, it's gonna be divided by 2.
correct, but what we're really digging into is the idea that reactions can't do math.
Yeah.
Reactions don't know what the K value is based upon molarity. And the answer is there's no relationship. What K is does not change relative to molarity, which I think is what Brandon was getting at.
So if you ever ask us a question, basically having us explain the reaction order, instead of, because if we try to explain reaction order in terms of math, we're gonna get it wrong.
No, so here's the thing. And guys, let me just tell you right now, you're going to see this in the Princeton Review book. So here's what we're doing. We're saying double the concentration, the rate doesn't change, that's a zero order reactant. We're saying double the concentration here, the rate quadrupled, that was a second order reactant. And we solve that logically, right? And guys, the logic is completely valid on the AP test. There is, however, a way to do it mathematically. And so what you would do, like if you were trying to find the reaction order for A, you would set this equal to 0, you would plug in the rate, you would plug in the concentration, and then solve it for the exponent, which involves logarithms. They will show you how to do that in the Princeton book, but you don't have to do that to satisfy the AP test graders. You can do this logically, you just have to explain it the same way we did, saying look at trials 1 and 3, when B doesn't change, A doubles, rate quadruples, therefore A is second order. You can do it logically, and then we don't have to do the logarithmic stuff. Okay, you guys good? Good? Okay, so guys, please do not take notes over anything that we're about to talk about. Just listen. Here's what we're going to talk about on Monday. Guys, how on stinking earth can that be? How can you have a zero order reactant? How can it be that you add more reactant to a reaction and it doesn't go any faster? And guys, the answer is this. When we looked at this reaction, we were simply told this, that A reacts with B to make C. And we understand that this is hypothetical, but it represents any synthesis reaction that we could want to talk about. But guys, here's the deal. This is kind of interesting, and you probably never thought about it. Guys, when you see a reaction, what's this stuff? The reactants. What's this stuff? The products. But guys, how reactants turn into products? We don't know. I like to think about it this way. This side of the reaction is like a birth announcement. This is like an obituary. But it doesn't tell you anything about the life lived. If the only thing that you had to go on was, hey, this guy was born and hey, this guy died, you don't know what happened in between. And guys, the same thing is going on here. When you're given a balanced equation, you have no insight into the behind-the-scenes stuff that's going on when reactant turns into product. And guys, that's what we're going to talk about on Monday. And we're not just going to talk about hypotheticals. How is it that A and B can turn into C? Because guys, it isn't just necessarily A and B running into each other and sticking and turning into C. Many times, it's much more complicated than that. And the complication comes down to what we call reaction mechanisms. So guys, this is what we're going to talk about on Monday. So guys, reaction mechanisms are the behind the scene processes that take place when reactants turn into products. So this is kind of fictitious, but the idea is this. So just like we saw in the thing, we saw that A plus B makes C. But what you didn't know is this. In order for A and B to turn into C, the first thing that happens is this. A falls apart. And then what happens next is the first part of A hooks up with B. And it makes a substance called A1B. And then what happens is A1B actually reacts with A2 to turn into C. And because that's what's going on in the background, it doesn't matter how much B there is, because guys, it turns out that the speed of this reaction doesn't depend on the amount of B, it depends on the amount of A, because in order for B to react, A's got to fall apart. So you can pump this thing full of B all you want and it won't go any faster because B is simply waiting for A to break apart. So, guys, that's what we're going to get into next time. Understand that we're going to get into more of the details later, but guys, that is the underlying complexity that we're going to talk about on Monday. The thing that explains first and second and zero and third order reactants is the fact that what you see is not what you get. It's way more complicated than that. And these steps that add up to what's really going on are called mechanisms. Now guys, let me lay this before you. Mechanisms are made up of what are called elementary steps. Guys, what does elementary mean? If you're in elementary school, what does that mean? It means can't be simplified. The very basic. So guys, mechanisms are made up of what we call elementary steps. Elementary steps are single step processes that add up to make the mechanism. Now what you're going to find out is that we describe elementary steps based upon the number of molecules that are reacting. So you can have what is called a unimolecular elementary step. That involves one thing breaking apart or rearranging. You can have a bimolecular elementary step, which is two things running into each other. And then you can have what are called termolecular elementary steps, where three things are running into each other. So given this idea, what is the molecularity of this step? It's unimolecular. There's one thing that is falling apart. What's the molecularity of that step? Bimolecular. There's two things. What's the molecularity of this one? It's not ter, it's bi, because this is one thing and that's two things. This is a bigger molecule, but it's still two things running into each other. Yes, yeah, so it would be A plus B plus C. Oops.
Oh, just treat it like terms.
Yeah, they're terms. Go ahead, Talmadge.
So in what conditions would all three run into each other at the same time?
And that's the problem. No, and that's exactly the problem. Because in order for two things, we'll do this again next time, but I'm going to have Dallin help me. See, in order for two things to run in together, they just have to hit, right? But now here's what we're going to do. We're going to hit, no, you only get one. We're going three. So we're going to go 1, 2, 3, and we're going to try to hit all at the same time. That was pretty close, but not quite. Oh, no, come on. Closer. Do you see the idea? Yeah, I am doing it on purpose, but the idea here, because guys, remember, we're conscious and we're trying to hit at the same time. That's exactly what you're going to find out, Talmadge, is that termolecular steps are really slow. Because in order for them to happen, what are the chances that three things collide simultaneously? It's almost zero. And you'll notice that we don't have a tetramolecular step. Tetramolecular steps where four things have to collide simultaneously don't happen at all. So the molecularity only goes up to 3.
Never happened.
What you'll find out in college is if you are given multiple potential mechanisms, the ones that contain ter and tetramolecular steps, you can typically throw out because they just don't happen. So.
There's never been like in a lab
Oh, no, yeah, so no, so,
Or is it-
yeah,
is it half
yeah.
nature?
But you understand what we're saying is that it's like shooting 4 guns at each other and having the bullets all meld together in the middle.
I mean,
Right.
more of an exact.
But could it happen? In theory, yes. But we'll say this. Mechanisms that act through termolecular steps are very slow reactions because those collisions don't happen frequently the way they need to. Okay, so guys, we are done. Here's your homework. This is it.